2 tries? All right. Math, probability.
Well, I got 6 tries too, so you want.
And I still don't get the last one. You only get there as quick as possible. Why don't we throw
2 trials for me.
We should throw darts at a dark one until we hit the hole, but that should be
That's not really. I guess it's probability. Not really.
That's more skill than luck.
If the dart is weighted in such a way that even if you throw it constant, it goes differently, then maybe. But
that would be
or like
just too much
spinning or something.
Yeah.
If we picked how someone else would throw it, that had poor skills,
They have fine motor issues,
Yeah.
and
yeah.
I don't know. I feel like that can't be probability though.
You know what we can do? We could do the Buffon's Needles activity, which is you have a circular region, so it's not quite a dartboard, but piece of paper with just a circle on it, and you just drop.
I was thinking about that for a board game.
Somebody actually did that. A student by the name of Emily Pickup. So she bought some pickup sticks and changed it to pickups sticks with an apostrophe. And it was very clever, and it was a good activity.
Does it matter if you put it in parentheses? Do you need to put like the last parenthesis?
It doesn't matter if you're just doing a single trial.
Oh, because then it took me like 25 tries to get 6.
All right. Oh, that's great. Oh, like I was hoping for stuff like that because I got it in 2, and that's not realistic. 6 is kind of like, what you would expect if all things were equal, but it doesn't always play out that way. All right. So what did you say you got there, Mike?
I'm still counting. I'm at like 16, 17, 18. 30 tries.
30 tries. That's great. All right. Sam, what'd you get? 6. Ah.
I got 4.
4 for George.
I got 2.
2.
4.
4.
6.
6. 9. 9. Right, 10. 40. 40.
Wow. You got beat.
So did that really happen, or you just said that to be the winner? Yeah. 7.
I win.
All right, so we have a pretty wide variety of values here. So
Okay, time for first.
So I'll just read the blurb here, but while in a binomial distribution, a random variable is the number of successes in a fixed number of trials. In a geometric distribution, a random variable is the number of trials it takes to achieve a success. All right. So in this case, I mean, it's like all over the place. All right. So we don't really know how many trials there would be. So to attack it using a binomial probability distribution doesn't seem to make the most sense in the world, but we could use some characteristics of a binomial distribution in order to help us figure that out. All right, so if you had a particular request or requirement, you could actually make a determination of a probability. So I could say, for example, so I'll just make a question here, the probability of getting a 6 in at most 6 rolls of a die. All right, it's completely experimental, but it's still something that you could at least start getting the makings of a solution for. All right. So we were just testing to see how long it would take before you got your first 6. But if we're looking to see if there's really a uniform distribution, what I would want is, on average, for the 6 to occur once out of every 6 times the die is rolled. Right? So now, for a small sample, only 6 rolls of die. I mean, that's not expected, but you can kind of start to see the makings of a solution here. So any outcome that happens in 6 or less rolls would be included. Yeah, so 6 out of 12, so 1/2. I'll write the 6 out of 12 though.
It would be 11.
It would be, but I participated.
Oh, yeah, I forgot.
He's a person too.
Yeah, I was counting the kids in our class. I forgot this
Teachers
was
are
there.
people too. We have feelings, hopes, and dreams. Nah, that's not true. Those have all been dashed completely at this point. Yeah. So, possibilities, I mean, we just went through one of them. And obviously, I mean, probability of getting a 6 and at most 6 rolls of a die, 6 out of 12, obviously that's not going to be accurate because we have a small sample. I mean, it could be accidentally fairly close to the right answer, but you know, we'd have to do this many, many, many times in order to get a true sense of what the probability would be. All right. So some examples of what a geometric distribution is going to bother me. Geometric distribution might look like: flip a coin until you get a heads, roll a die until you get a 6, which we just did, throw darts at a dartboard until you hit the bullseye. All right. That last one's a little iffier because of what we were talking about before. A little bit of skill is involved, unless you're completely doing it at random, in which case I don't even know how that could be executed safely.
You could be blindfolded. But
Yeah,
not really.
that's what I was thinking. I'm like, somebody would still have to aim you in the direction of the dartboard, even if you are blindfolded.
What
So
we could do is we could just put the bullseye on a random part of the dartboard, like give all the parts of the dartboard different numeric values, and then not tell whoever was throwing which part the bullseye was.
So equal areas to account for the different probability.
I think that still takes into account the skill and also the like
I mean, yeah.
mindset of is someone going to just like hit a bolt like one number a ton of times, or are they going to be logical and try and hit a ton of numbers, or I don't know. It
Oh yeah,
works.
because if they start aiming for things.
Yeah.
Yes.
I mean, that still has some skill, but it's less than just if they know where the bullseye is. So.
Either way.
I'm just thinking that the only way to remove any kind of bias from it that I can think of would be to create that same scenario, but then have a random simulator just randomly select numbers associated with the different regions. So where's the fun in that? You don't even get to throw a projectile across a room. Like why even bother?
Have the computer do it.
You know, so you might as well just spin a spinner. So, geometric distribution has to have these properties. Each trial in the experiment must have only two possible outcomes, success or failure, so same as binomial. Probability of success does not change from trial to trial, so same as binomial. The trials in the experiment are independent, so same as binomial. The variable of interest is the number of trials required to reach the first success. So that's the only thing that makes this different from a binomial distribution. So, not a fixed number of trials. All right, so kind of like, a loose example would be the difference between taking a test here and maybe taking a test in Mr. Nuscazy's physics class. Because you get a couple of different cracks at taking the test, if I'm not mistaken.
3 and M, yeah.
Yeah.
You get 2.
Oh, you get 2. Okay, so maybe it's not completely geometric, but it's not one and done. All right. How you do on the first go around dictates whether you need to take the test on the second go around. So failure on the first attempt indicates an attempt is made a second time. For me, well, failure on the first attempt
Is failure.
is just, yeah. So, well, that's just depressing. So let's move on. All right. So we're going to find various probabilities associated with our dice simulation, come up with probability distribution. So A, probability that a 6 will come up on the first roll is 1 out of 6. That's easy enough. The probability that a 6 will come up on the second roll is the probability that it won't come up on the first roll and that it will come up on the second roll. So failure, then success. And so the product of that gives us 5 out of 36, not difficult. The probability that a 6 will come up on the third row means that you got failure on the first and second attempts and success on the third attempt. All right, and so you multiply those probabilities and you can see that what you're ending up with is a lot, potentially, like in the case of 30, 40 outcomes where it took like the 40th trial to get a success, that would mean that there would be 39 5/6s, and the last multiplier would be the 1/6. That would be the event that the individual successfully got the 6. Right? So you can see how this could get kind of out of hand in terms of the calculations, but as long as you have a general sense of the structure, I don't imagine that there are going to be any people that are typing in 5/6 times 5/6 times 5/6 times 5/6. You're going to use powers. And so that's the whole idea. The calculator actually has a function, a geometric distribution function, but this is one of those instances where I think it's a complete and total waste of time, and I'll show you why. But before we do that, I have to fix this table for you because it looks stupid, because for whatever reason, when I was converting the format, it changed all my multiplication symbols to quotation marks, which is completely aggravating. So another typo bonus opportunity for somebody. All right, so in this table, we get to the idea that if I'm going to get success on the first trial, it's just a 1 out of 6. Every trial after that is accounting for all the different ways in which you could fail, which 5 out of 6 accounts for. And then the very last entry is the probability of success. So the N, if I'm looking for probability that my first success is on the nth trial, that means I failed N minus 1 times. So 100 trials, I failed 99 times. That last trial would be my success. All right. And so that gives me this distribution, a skewed right distribution in all cases, assuming that it's more likely that you're failing than succeeding. And that's specifically associated with games of chance. It could be the other way around, but generally, if something positive has a likelihood of happening, then we're not overly interested in investigating the probabilities. All right. So if I have a big chance, a big probability for something not succeeding, then I would expect that the probability that my number of rolls, or the probability that it would occur on my, for the lower number of rolls, to be significantly larger than for the higher. All right, because again, this is saying that it's going to take like 10 rolls before I get a 6. 40 rolls before I can get a 6, 100 rolls, those probabilities are going to decline significantly as I go out. Because if you just think about it, in a practical sense, I kind of, people talk about it all the time in sports, like the idea that something is due. Right? So, a good free throw shooter in a basketball game, apparently R.J. Barrett is not one of those. But let's say he was. And normally he shoots 90% free throws. Not true, he normally shoots 60% free throws, which is terrible. But let's say he was a 90% free throw shooter. And throughout the course of a game, he just missed 7 consecutive shots. A person might say, well, he's bound to make one at some point because his performance has to match his population statistics, his population parameters. All right, so what you would end up walking away with is the idea that he's due. He's not going to miss all of them. At some point, if he really is a 90% free throw shooter, his performance has to balance out that streak of losses. Same thing in in a baseball season. You have a really good team, Houston Astros, Yankees, anybody but the Mets, I guess. God, I love the Mets, but man, they suck. But you know, like a good team like the Houston Astros, who you know are going to win a lot of games, but they're in the middle of a 10-game losing streak, right? At some point, the probabilities have to start balancing that out, because if they really are a good team, then they're not going to just keep losing. At some point, they're going to start winning. All right, that's the idea here. You're looking at a 1 in 6 chance of getting the outcome of 6. The more trials that go on without me getting that outcome of 6, the more likely that number is to come up. All right. So that's really what all of this is saying, and you know, giving a guided example along the way. All right. So it's pretty straightforward. So let's actually go back and take a look at some of our extreme examples. So probability that x equals 30 and probability of x equals 40 in the geometric distribution. All right, that means that we failed 29 times and 39 times respectively. And we succeeded on the last trial. So 5 out of 6 raised to the 29th. 1 out of 6 raised to the first if you want, but it's just 1 out of 6. So we get that. All right. So 0.000843. All right. Same calculation, but this time to the 39th power. 0.000136. So very, very minuscule probabilities. So those calculations, not difficult. So you might wonder why we would need a calculator function for it. I don't think you do, but I'll show you where it is anyway. Second vars, we have geometric PDF and CDF. All right. Oh, and then the Poisson distribution, which we're going to get to tomorrow.
What is F? This is FGDF.
F distribution.
A lot of different distributions. The squiggly X squared.
Squiggly, what?
All right, so geometric PDF, you put in the probability of success on any one trial and the number of trials that it takes before you achieve success. And it'll compute it for you. But this isn't like binomial probability where you need combinations and fractions raised to powers and things like that and multiply it all together, at least and at most and all that good stuff. It's not hard to do it this way. And honestly, I've had people during a test say, I can't remember how to do it in the calculator. And then I would say, well, then just do it by hand. And they'd be like, oh, wait a minute. Oh, wait, no, forget it. Forget I awed. Because it's actually really easy to do by hand. Forget it. Yeah, I didn't even need the calculator thing to begin with. All right, so this is one of those rare instances where I think you could probably just disregard the calculator approach, right? The geometric distribution, it doesn't really bring anything to the table, right? So But it's up to you. If you like just knowing what every function in the calculator represents, then that's probably not the worst thing in the world. All right.